Welcome to my channel. In this video, we shall be looking at rotational motion. In my earlier video on rotational motion, we looked at rotational motion, tau, angular momentum, principle of conservation of angular momentum, and moment of inertia. I encourage you to please watch that video. The title of that video is Rotational Motion 1. So here we shall be looking at rotational motion 2. In this video, we shall look at the following. We shall consider rotational kinetic energy of rigid body. We shall look at rotational and translational kinetic energy of a rigid body. We shall also consider rotational kinetic energy of a rigid body on an inclined plane, and we shall solve problems using the expression we shall derive for kinetic energy of rotation, kinetic energy of translation, and the gravitational potential energy. Recall that rotational motion is a motion of a body or object in a circle about a center or axis. So the motion of a body or an object in a circle about an axis is called rotational motion. So let's look at kinetic energy of a rigid body. Consider a rigid object of mass m rotating with uniform angular velocity about an axis passing through its center. So if we have a body of mass m that is rotating with uniform velocity, uniform angular velocity through an axis AB. So the object possesses kinetic energy due to its motion, and this is called rotational kinetic energy. So this body of mass moving with uniform angular velocity omega, as it is rotating about its axis, it possesses kinetic energy. And this kinetic energy, we call it rotational kinetic energy, which we represent as this. So recall that kinetic energy is given by, let's call this equation 1. So this is the kinetic energy of an object moving in under linear motion, moving on a straight line. But we have already established from the relationship between linear velocity and angular velocity. So the relationship between linear velocity and angular velocity is given by equation 2. So if we take the square of it, giving us equation 3. So if we put equation 3 in equation 1 in place of V, we will have that the kinetic energy will be given by equation 4. Also, we have established that moment of inertia is equal to this. In the last video I just referred you to, all these have been explained here. Please, I advise you watch the video for more understanding. So moment of inertia is given by equation 5. So if we substitute equation 5 into equation 4, we will have kinetic energy to be equal to equation 6. So equation 6 is the kinetic energy is the rotational kinetic energy of an object moving in a cycle about a fixed point. Here, this is the angular velocity. This is the moment of inertia. So this expression, we use it for what? Calculation of kinetic energy of rotation of a rigid body. Remember, we are looking at kinetic energy of a rigid body. So this expression, we use it for kinetic energy of rotation of a rigid body. Why this is the kinetic energy of an object moving on a straight line. I hope that is taken. Okay, let's make progress. It is possible that an object is rotating at the same time translating. For instance, you have let's say the tire of a motorcycle. You see it rotating with angular velocity omega, and at the same time is translating with linear velocity. So, certain motion can easily be described by combining translational motion as well as rotational motion. So this is an example. The tire, let's say, of a vehicle, the tire of a motorcycle, as it is rotating with angular velocity, it is also translating. So it has angular velocity with which it is moving, then it has linear velocity with which it is equally moving. So in the case of a motion like this, we are combining translational motion with rotational motion. So the kinetic energy, the total kinetic energy of an object that is translating at the same time rotating is equal to kinetic energy of rotation plus kinetic energy of translation. And we have established that kinetic energy of rotation is given by this, while the kinetic energy of translation is given by this expression. So, for an object that is rotating at the same time translating, it possesses both kinetic energy of rotation and kinetic energy of translation. I hope that is taken. Okay, let's look at another scenario. Let's look at rotational kinetic energy of a rigid body on an inclined plane. If we have a rigid body of radius r that is inclined to a plane of height h at a distance s at angle theta, we can say that the weight of the body is given by this, and this object possesses rotational kinetic energy and also translational kinetic energy. So as the object moves down the inclined plane, it possesses rotational kinetic energy by virtue of its motion, possesses translational kinetic energy, and also by virtue of its position, it possesses gravitational potential energy. So for a system like this that is not sliding, the kinetic energy possessed by this object One is gravitational potential energy, translational potential energy, and rotational potential energy. So the system, such as a bowling ball rolling down a ramp, is described by three types of energy. So we have the gravitational potential energy, translational kinetic energy, and rotational kinetic energy. So all these forms of energy plus potential energy of any other conservative force must be included in our equation for the conservation of mechanical energy of an isolated system. So for this system, we can say that from the conservation of energy, that the kinetic energy of rotation plus kinetic energy of translation plus gravitational potential energy initial will be equal to kinetic energy of rotation, kinetic energy of translation, potential energy, gravitational potential energy. Let's call it final. So for a system like this, we say that the energy, the initial energy must be equal to the final energy. So this is the principle of conservation of energy for an object like this. So the relation is true only if we ignore dissipative force such as friction. So this equation can only be true if we ignore dissipative force such as friction. And if the body is not sliding down, if it is just rolling down, then this conservation principle holds. So let's look at some example of how we can apply this principle for rotational kinetic energy of a rigid body on an inclined plane. So let's look at example. Let me read out the equation. A 500 uniform sphere of 7 centimeter radius spin at 30 revolutions per second on an axis through its center. Find its kinetic energy, angular momentum, and radius of gyration. Solution. Let's look at the given parameter. The radius was given. If we convert, we will have this. The mass was equally given 500 grams, which will be equal to kilogram. Then the angular velocity is given 30 revolutions per second. So we need to convert this revolution per second to radians per second, which is the SI unit for angular velocity. So how do we do that? We know that one revolution is equal to this. So 30 revolution will be equal to S degree. So from here, X will be which will be equal to 10,800 degrees. We are not looking for the answer in degree, but radians per seconds. But we know that 2 pi radians is equal to 36 degrees. So x radians will be equal to 10,800 degrees. So from here, we will have that 2 pi times 10,800 over 360. So we will have the angular velocity to be 188 radians per second. In my video on rotational motion 1, I explain all this. So please, you can equally look at it for more understanding. So we have gotten these parameters. The next thing we need to get is the moment of inertia. A moment of inertia varies based on the shape of the object. So for a uniform sphere, this is the moment of inertia. So let's substitute the mass of the object, 0.5, so if we simplify this, we will have this. So with this now, we can start answering the question. The first question says we should find the kinetic energy. Since the object is rotating, we use kinetic energy of rotation. What is the formula? Do you remember? Yes, this is the formula. So let's substitute. Substituting and simplifying, we have the kinetic energy to be 170 joule. Is it difficult? The second question says we should find the angular momentum. Angular momentum is given by this expression. Angular momentum equal to moment of inertia times the angular velocity. So let's substitute. If we substitute and simplifying, we will have the angular momentum. Then the last question says we should find the radius of gyration. So already we have established the moment of inertia is given by this expression. So from here, making K the subject formula, we will have this. And if we substitute and simplify, we will have 0.044 meter. So it's as simple as this. So for this problem, all we need to do, bring out the given parameters. The ones that are not in SI unit, you convert. Then the SI unit for angular velocity, like I told us, is radians per second. So it was given revolution per second. So we have to convert from revolution per second to degree, from degree to radians per second. Also, the moment of inertia of a uniform sphere given by this formula. So we simplify and we have this. So from here, the next thing, kinetic energy of rotation. We have already derived the expression. So when we substitute, you have kinetic energy of rotation to be 170 joule. Is that taken? Then angular momentum. This is the expression when we substitute moment of inertia that we computed earlier. Then angular velocity that we computed to be this. When we substitute, simplify, we have this. Then for the radius of gyration, this is the formula. When we substitute, this is the answer. I hope there is no challenge. All we need to do, convert to the SI unit, then know the formula to use and substitute. Okay, let's look at another example. Example 2, let me read out the question. A ball of mass and radius start from rest at a height of 2 meters and roll down a 30-degree slope. What is the linear speed of the ball when it leaves the incline? Assume the ball rolls without slipping. Solution: we have a ball of mass m, radius r, and it is inclined on a plane at the height 2 meters. And at an angle 30 degrees. So we have to find the velocity as the ball rolls down. So applying conservation of energy, we have that kinetic energy of rotation plus kinetic energy of translation plus gravitational potential energy initial is equal to kinetic energy of rotation, kinetic energy of translation plus gravitational potential energy. So, applying the conservation of energy, we are saying that as the body is on the inclined plane, it has kinetic energy of rotation, translation, and potential, the initial one. As it is rolling down, it also possesses that energy. So according to the conservation of energy, is that the initial energy possessed by the body on the inclined plane will be equal to the energy possessed when it rolls down. So as the object is on the inclined plane, when it is stationary, the kinetic energy of rotation is 0 since it is not moving. The kinetic energy of translation is also 0 since it is not moving. However, it possesses gravitational potential energy. And as it rolls down, it has kinetic energy of rotation plus kinetic energy of translation, while the gravitational potential energy is 0 because it is moving. So the formula for gravitational potential energy is given as this, and the formula for rotational kinetic energy is given as this, while for the translation is given by this. So the next thing we want to do, the I here, moment of inertia, says a ball is fair. So we put the moment of inertia, which will be given by this. So we have substituted moment of inertia. So we can simplify this. If we simplify, we will have 7/10 mv squared. From here, since the mass is the same, we cancel out. The velocity, make v the subject formula. From here, we will have 10 gh over 7. And if we simplify, 10 times 9.8 times 2 over 7. So we will have 5.29 meter per second. So for this object that is rolling down, all we did here is to apply the principle. And the next thing is to substitute. Moment of inertia for a sphere is given by this expression. So if we simplify this, open the bracket, we will have this. And since the mass is common, we cancel out, making V the subject formula. We have this. G is the acceleration due to gravity, 9.8. Then the height is 2 meters. Are we together? So if we simplify, this is the velocity of this object, the linear velocity as it moves down the inclined plane. I hope that is taken. Hope it's not difficult. Okay, so let's look at another example. This will be our last example. Example 3, let me read out the question. Starting from rest, a hoop of 20 centimeter radius rolls down a hill to a point 5 meters below its starting point. How fast is it rotating at that point? Solution. The radius of the hoop is what? 20 centimeter, which is equal to 0.2 meter. The height of the inclined plane is 5.0 meter. Then, applying principle of conservation of energy, we can say that the kinetic energy of rotation plus kinetic energy translation plus gravitational potential energy initial is equal to kinetic energy of rotation, kinetic energy of translation plus gravitational potential energy final. So, as the hoop is on the plane, the rotational kinetic energy is 0, translational kinetic energy is 0. It only possesses gravitational potential energy. And as it rolls down the plane, it has rotational kinetic energy, translational kinetic energy. However, the gravitational potential energy is 0. So, from here, Gravitational potential energy is given as this. Rotational potential energy is given by this, while the translational potential energy, kinetic energy, is given by this expression. So from here, we know that from the relationship between linear and angular velocity, we have this expression. So if we square it, have r square omega square. And also, moment of inertia is given by this expression. Note that the radius r is equal to k square. So from here, if we substitute, we will have half m r square omega square. So if we simplify this, we will have this expression. So if we simplify further, so the mass will cancel out. We are looking for angular velocity. So making a subject formula, we will have this expression. And if we simplify, we will have this. So the angular velocity will be 35 radians per second. So all we have to do here, bring out the parameters, convert to the SI unit, then applying conservation of energy, that the kinetic energy of rotation plus kinetic energy of translation plus gravitational potential energy, the initial must be equal to the final. And when the body is stationary on the inclined plane, the rotational is 0, translational is 0. It possesses only gravitational potential energy. Then, in the case of the final, as it descends, as it rolls down, it has kinetic energy of rotation and of translation. Potential energy, gravitational potential energy is 0. So if we substitute, we have already established the expression for this. So if we simplify, knowing that linear velocity is related to angular velocity using this expression. So if we square it, we will have this. So coming to this expression, in place of this, we substitute this, then we have this. I hope you are following. Then, the moment of inertia here is expressed as this. So from here, if we substitute moment of inertia, substitute this in place of it. See it here. Are we together? Then when we simplify further, knowing that r square is equal to k square. So we replace r square with k square. And from here, if we simplify this, we will have this expression. Since the mass is common, we strike out. The next thing, we make angular velocity subject formula. And when we do that, you have this. Then we substitute. G is the acceleration due to gravity, giving us 9.8. Then the height is 5 meters. Are we together? Then the radius is 0.2. So if we substitute and simplify, this is the angular velocity of the hoop as it rolls down the inclined plane. So thank you very much for watching. Please like, share, and subscribe to my channel for more interesting videos.